All right, our study of calculus begins. We're going to dive into section 1.3 and we're going to introduce the notion of the limit of a function. And this is really the heartbeat of what calculus is all about. Well, most of the functions that you've seen so far in your mathematical career are sort of nice somehow. They typically have either clean formulas, relatively clean, or at the very least clean graphs. And when I say clean, I mean continuous and everything is sort of nice. So two quick examples. Classic would be f of x equals x squared, or maybe even something where the formula is a little bit more interesting. Whoops, my sine wave got a little carried away there. Formula is a little more interesting, but the graph is still really nice. So this would be like sine of x. Roughly, it's a little bit off, but close enough. Okay, and so the point is that not all functions are so nice. And I want to look at the Dirschlage function. I believe I'm pronouncing that correctly. And it's defined as follows. So you plug in any number that you want. You plug in any x that you want into g of x. And g of x outputs 1 if your function is rational. We denote the rational numbers with q. And 0 if it's not rational. So for example, let's just write down a few things. So g of pi, what would that be? G of pi would be 0, g of 2 would be 1, and so on and so forth. And so when you go to graph this thing, if you realize how tightly packed the rationals and the irrationals are, then the graph almost looks like it's not even a function. You're going to see this horizontal line at 1 and this horizontal line at 0 as well, and they're so tight together that it looks like two lines here and here, but in fact that's not a function. It would fail the vertical line test. That's not actually the graph. It looks like a line, but remember there's little spaces between the zeros and the 1, and so this is a function, and yet it's an extremely messy function, both in formula and in graph. And so the point is many functions that we need to model the real world and applications, so on and so forth, they're not so nice. We need to learn to deal with the not nice situations. And so our goal in this section is to develop tools to understand the behavior of a function at a specific point. And we're often interested in the points where the function isn't defined. And if you think about it, that's kind of a rather daring thing to do. The function is not defined. How can we possibly learn anything about it? It's undefined there. Well, let's look at this example together. So I want us to consider the function, let me zoom in a little bit, f of x equals x cubed plus x squared all over x. And so it's not hard if you think about the rules that we talked about in the review. The domain of f is, well, I just can't plug in 0. So the domain of f is, let's write it this way. We'll say it in interval notation, minus infinity to 0, union 0 to infinity, right? This is the same thing as the set of x in the reals such that x is not equal to 0, however you want to write it. Okay, so the question that we want to understand is what happens at 0. And on the one hand, we need to realize that f of 0 is undefined. That's it. The function is not defined there. You can't talk about f of 0. And yet, there's more to the story. And so what I want to do is switch the screen to Mathematica, and we're going to try and understand the behavior of f at 0 by studying how it behaves for values near 0. So let's switch the screen. I'm going to pull Mathematica up, and we'll run some numbers together. All right, well, welcome to Mathematica. When you click on the Mathematica icon, this little box pops up, and you just want to go ahead and click on New Notebook. And so I'll put that in the corner of the screen. I'm going to zoom in a little bit to make it easier for you to see. So Mathematica works in cells, and so to make a new cell, just click anywhere your cursor goes sideways, which I've done, and then I can begin typing. And I want to make a new function, so I'm going to write f, and then you do square bracket, and then your variable needs to have an underscore next to it. So that's saying make a function f that's going to have variable x, colon equal, Now, there's different ways you can type the function in. If you want to make it look nice, you can click on Palettes and then Basic Math Assistant. That popped off the screen, so let me drag it back in here. So this has all kinds of fancy features, but I can simply click on the fraction button and then the exponent button, and now I get an x cubed, and we can scoot over and say plus, and then we'll say x squared all over x. And so that makes it look really nice. Now to enter it, you can't see my keyboard, but I actually have to enter this into the computer. And the regular enter for your alphabet doesn't do the job. You either have to use the enter for the number pad or shift enter on the alphabet. So I'm going to click either one of those, and now I've punched it in and it knows what it is. I can plug in things. I can ask it to tell me what's f of 1 now, and it'll do the math and tell me that f of 1 is 2. So it's really a fantastic way to compute things, much easier than doing it by a calculator where you're re-entering the form again and again and again. All right, so we're interested in what happens to this function near 0. And so we can ask it, well, let's just see, what is f of 0? And it doesn't like it. It says indeterminate. So we can't just plug 0 in, but we can try plugging in things close to 0. And so let's see about f of, let's just say 0.5. f of 0.5, I get out 0.75. Now I can say f of 0.1, I get out 0.11. So that's interesting. The value is going down. I'm at some point going to need to be able to keep track of digits. So let's find out when. If I go 0, 1, I get that small value. So wow, as x gets close to 0, f of x is getting awful small. Let's add another 0, getting even smaller. Add another 0, getting even smaller. Another 0, it just keeps getting smaller. We keep adding zeros. Okay, it's switched to scientific form, so let's try decimal form, and then I think we can actually ask it to carry a bunch of places. So let's say, let's ask it to carry it out to 40 places for us. Is that enough? Yeah. So there it is. Now we're back to decimal form. We can just keep letting x get closer and closer to 0, and boy, you can see the function is getting closer and closer to 0 as well. So it doesn't matter how many zeros I add, the output is getting closer and closer to 0. So when you put in x values close to 0, you get out a y value that's very close to 0 as well. So let's switch back to the other screen, and then we'll write down what we found. So based on what we saw in Mathematica, even though the function is not defined at 0, f of 0 is undefined, it seems that f of x is getting closer and closer and closer to 0. So we can at least say this. We can say f of x is going to 0. I'll use an arrow to indicate that. F of x is going to 0 as x goes to 0. We're not saying f of 0 equals anything, but we can say as you get close to 0, the function is getting closer and closer and closer to 0. And there's an algebraic way to sort of see this. And so if you realize that our function here, hopefully you've noticed this already, there's a common factor of x everywhere. We can actually cancel this and say, look, this is actually x squared plus x as long as x isn't 0. So you can't say it's always x squared plus x because I can only divide the x out when x is not 0. But it is equal to x squared plus x when x isn't 0. And now this function, were you to plug 0 into it, you would get out 0. And that's exactly what's happening. The graph of this function, as we'll learn a little bit later, has a hole in it. Whatever the graph looks like at 0, there's just a hole sitting there, and the function is doing something like that. And the hole is, we could fill it in if we wanted to and make it 0. So that's our first example of studying the behavior of a function at a point where the function is undefined, and yet we realize that, yes, the function is undefined at 0, and yet it clearly has a behavior at 0. It's getting closer and closer and closer to 0. There's a sense in which we could define it to be 0 if we wanted to. So let's end this video here, and in the next video we will do some rock chunking, one of my favorite things to do.